I'm talking about this project on behalf of the collaboration, which consists of several countries. I will show later. Okay, the outline of my talk is following. So just let me start with some prospects of future gamma-ray burst mission and present limit in optical observation. I will talk about UFO pathfinder onboard Lomonosov spacecraft. The first is a sling mirror telescope, we call. That's the key of UFO to explore the new time domain. The another one is, the fifth bed like UFO bed, we call the U bed. That's for the localization of gamma-ray burst, including faint, soft, nearby GRB and high redshift GRBs. I will come to the summary. As for the prospect of gamma-ray burst physics, I think in this community, I think everybody is eager to study the origin, in terms of progenitor or central engine and jet dynamics, progenitor environment, etc. So let me show the next slide here. Well, this is well on the fiber model afterglow. This is given by Dine. The afterglow is very important, no matter what the central engine or no matter what the progenitor is. Here you see the previous speakers already talked about this all types of emission here, internal shock and the external shock. Well, the emission of the high energy gamma rays are produced from the internal, the collision within this at the very high range factor, and then this jet is eventually collided with the ambient medium to generate the external shock, which gives you all types of electromagnetic radiation. Well, this is timing, and the light curve is depicted in this plot here. This is timing and the flux, and then there are a lot of internal, very short variability, which represents the internal, shock wave, and then some plateau, and there is afterglow, and so on. And also the short GLB, dark GLB. Well, this is still, data statistics is poor. So I think we need to understand such, also very tantalizing, the gamma-ray burst, categories. Well, if we are lucky, and then there is an exotic source like, fast transient cosmic ray flash like primordial black hole or, dark matter accretion. This is another, very exotic candidate for the GLB. Well, one of the great, one of the most interesting features of gamma-ray burst is a potential candidate for the standard candle. Well, certainly we will see if this can be calibrated. Well, for example, there are so many people working on the ePIC, time lag, and ISO, and so on. And then maybe a couple of years ago, the rise time correlation entered this game, whether we can calibrate the gamma-ray burst or not. Well, certainly there are many disputes or some the dispute, but we still see, still interesting. Well, GLB is the most energetic explosion in the universe. That's why this is time history of the universe. As you know, the Big Bang afterglow, dark age. There is no shiny object here, and then at a certain time, first star and the galaxy must be created here, and then this material stars and the galaxy re-ionize the universe again. Well, this is we call the re-ionization epoch. So in terms of redshift, I think the supernova can reach the typically redshift 2, maybe the principally 3. However, the GRB is so bright, and then we already see the GRB at the redshift about 6.7 or so. And then we hope, actually, we like to see the GRB up to 12 in near future, but in principle, actually, over 15, for example. So the GRB has a great leverage in time, so it's a very good tool to study the first star formation and also re-ionization epoch. So that's early universe study. And then the concerning extreme universe, gamma-ray burst is related to the black hole. So we hope to study the event horizon and gravity, shock breaker, and so on. Also, you can test the range invariance and CPT violation if you measure the multiband very precisely. Also, the synaptic astronomy, multi-dimensional astrophysics, this is also important because the GRB, produce the neutrino, not only the electromagnetic radiation, neutrino and gravitational wave, and then this gives the unique, the opportunity to do synaptic astronomy and the multi-dimensional astrophysics. Well, I would say, so these days is renaissance of GRB. There are many missions were flown, and also still Swift and Fermi still in operation in space. Swift is launched in 2004. I would say this is a GRB dedicated mission because the Swift they generated the so-called LAT, the GCN, to the ground telescope for the follow-up, the observation. There are actually not the GRB dedicated, but there are so many actually X-ray missions, Bevel-Sachs, integral mesh, and so on. Also, there are a bunch of ground telescopes as well for the follow-up observation. In the near future, what will be, well, the UFO Pathfinder, which I will talk in a minute, and Swarm, this is Chinese-French mission, will be launched in 2017, hopefully, and the Spectrum Gamma, well, I don't know the schedule, but very soon, Janus Polar, etc. This is still under queue. Well, we hope there are a lot of instrumental progress in future missions. Well, because it received one run forever, because it will end its mission in near future. Well, we hope a lot of improvement in terms of flux, color, and time. The flux is sort of a photometry, the color is kind of a band, and the time is temporal, the temporal structure of the GRB. So we have to improve the sensitivity, well, by lowering the energy, by the faster the response time, and then also the precision of the photometry and so on. Also, we need a large bandwidth anyway for the future missions. So in order to do it, you need a higher sensitivity in photometry, wide energy band, with lowering energy, rapid time response. Well, this means you need a large, finer, faster detection telescope. Probably you can argue which way is best, in the future. Well, the giant mission, space mission like a Swift, or small missions dedicated for a particular subject and so on. I think they can be arguable. But nevertheless, we need future missions. So I think most of people are interested in the high redshift gamma ray observation for the early universe probe. Well, this is very important, as I told you before. This is important for the study of first star, galaxy, reionization, dark age, etc. In order to do it, you need the infrared observation in space. Actually, in the ground, there are some telescope has such functionality, but in space there is no IR or near IR measurement so far. Also, you need a very high sensitivity in X-ray, at least less than the 10 keV. Hopefully, 5 keV or even lower to measure the very high redshift GRB. Another subject is we like to see the early photon as early as X-ray. Well, this is also important for the study of progenitor, powering shock, radiation classification, and so on. Also, short GRB, dark matter accretion, primordial black hole. Well, all the time scale is very short. Well, certainly it's order of 100 milliseconds or 1 second. So I think certainly, fast is certainly better. So you need a rapid response during technology. Another one is important for the future mission is polarization measurement for not only from the X-ray but also UV and optical. I think this is also open instrumental the regime to be improved. Okay, this is energy spectrum. Here you see this is energy, and this is flux. This is X-ray measurement for the different timing beams. Here you see this is optical measurement, the 3 optical regime here. This is famous, the 2008 GRB, 08 or 0319B. Well, they have a very nice, the measurement of the optical here, but this is 4 orders of magnitude higher. Well, probably this is a completely different, the physical origin from X-ray and optical, for example. Well, this is another measurement. So, but here you see only one optical, measurement in the data. So probably if you provide the infrared or near-infrared data here, this will give a lot of information. So you need the multiband observation in optical needed. The correlation between the X-ray and optical, well, this is very, very old data, but it's still useful to see. This is X-ray. This is time light curve. The X-ray and the dot is optical. This is probably, but there are only few points here. But this is no, correlation. Well, this is famous, again, 08, 03, 19B, GRB. This is mostly, correlated. So there are, the optical and X-ray are probably correlated. So, well, Rakushin et al., they actually claimed that this is more or less the same origin, just using the synchrotron radiation and the SSC whatsoever. But there are another, the many discussions, because there are somewhat delays between the X-ray and optical. Well, I think there should be a lot of discussion to explain why there is. Anyway, the correlation or delay of light curves from different range will give you a physical linkage between emission process. So correlation of early optical and the gamma, well, but I would say those are sort of accidental measurement, because here, this is very nice, very precision optical data is provided here. However, this is we call the lucky, burst, right? This is, you cannot wait another 10 years to see such a, very nice measurement. So we need a very precision measurement in optical, also very early, photon measurement. That's clear. Okay, in the robotic telescope on the ground, I think Roche, particular Roche 3 is one of the fastest robotic telescopes. They provided such a, light curve, X-ray, and this is blue is their measurement. No, sorry, the red color is their measurement of the optical. But here you see there are some correlation. It's very hard to judge, hard to estimate what's going on, particularly for poor precision in the optical measurement. So you need early time measurement of optical. This is again, this is some of the old data of light curves as a function of time and the magnitude. But here you see this is 60 seconds here. So even though there are some data, but only one couple of points here. So data quality is poor, I would say. Also, there are not many data. Here you see there is no rising phase was made, was observed here. So here you see the huge variation in light curves. So we don't know what the prompt optical emission. And in some data, there are no rising phase of light curves. So you need event statistics. Also, you need very high precision data in the optical measurement. So rising time of optical is very important, because the forward shock emission, well, this peak time of rising optical light curves gives you the estimate of initial range factor. So here you see this is the peak time and the range factor. Well, certainly well, 1,000 of range factor, well, it corresponds to the peak time is about 10 seconds. So I think you need the early time measurement as much as possible. This is give a good help. The rising light curves are almost important to understand the onset of optical, as you know. This alpha, well, the more or less 2 or 3. This is more favorable, but still you need the precise measurement of this rising light curves for this onset of optical. And also you like to study the off-axis, the substructure off-axis, the observation is related to the rising time dependence. So rise time is also, the optical rise time is also important for the cosmology. Well, Barnard-Teske and Westrang a long time ago, they suggested they might be, well, this is very argumentable, but they might correlate with the luminosity. So however, the data statistics is still poor, so you need the more data at the early time. And also here you see the most of the data has no the rising phase. So basically we are interested in this rising phase at the early time. Okay, there are some other, the subject. Well, the the X-ray is, we have a lot of the variability, but here we don't know exactly, what's going on the optical. Actually, optical, they have the same variability or no, whatever. Actually, there are some data, but there is no chance to make some conclusion concretely. So for the shock and the reverse shock, also so these people, they suggested, the reverse shock and the forward shock. That's what we see here. But in general, reverse shock feature is not clearly visible at optical frequency, even though there are some publications, they called it the reverse shock feature here. But it's not clear at the moment, what's a mixture of reverse and forward shock. So once you have a very early photon measurement, I think it gives you a lot of hints how to what's going on this reverse shock and the forward shock. Well, this is dark burst also. Well, everybody believed that this dark burst believed to be a circumstellar extinction of Lyman alpha absorption. Well, but I don't think this completely rule out whether the host is obscured or highly redshifted, or I think the GRB itself is faded out too fast, optical is faded too fast, who knows. Actually, this is the peak time, redshift calibrated peak time, but that's this rise time. Well, I think there are some correlation or not that we'll see. I think here you see the very high, very large, rise time. Usually, the occurs at a very fast peak time. So you need a very measurement of a very early rise time here, and then you see the rise time. You can measure the rise time more precisely. And the short half GRB and the very short GRB and so on, the time scale is very, very short. I think the order of second or order of 100 millisecond. So I think the early time measurement is actually very important in the future. Okay, the motivation of the early time measurement is coming from this plot. This is number of UV optical measured by a SWIFT emission as a function of time after the trigger. Well, this is only the UV optical measurement. Here you see the typically 100 second is peak time, the central value here, and then it falls off rapidly with the almost cut off below the 60 seconds. So I would say this 60 seconds is a practical limit from the SWIFT. So we don't know what's happening at the short time scales. Well, this Roche response is the response time. This is a fraction of GRB. Here you see even though they they do have a response as early as 20 seconds, but fraction is very, very small. So if you need a large amount of data event sample at early time, I think we need a dedicated the fast response instrument. Well, SWIFT is really SWIFT actually. We believed so far. Well, Peppersax is, we would say, first Egyptian space telescope, as everybody knows. And the SWIFT is actually first pointing telescope because they, rotated their entire spacecraft to the GRB position, but it takes typically 1 minute. That's why the swing limit is at the moment is 1 minute. So. Is it possible to beat this 1 minute barrier from space? Well, we like to propose the first sub-second response telescope. Well, this SWIFT, well, this is what the SWIFT they do. Actually, instead of slewing the entire the spacecraft, you can move the optical path. Not the spacecraft with the fast slewing mirror system. This is just a simple slewing mirror system. This is just mirror, plain mirror, and in front of a telescope. And then once you get a trigger from so-called X-ray, and then you just rotate this mirror. This is much faster than the rotating the spacecraft. So you can achieve the slewing speed down to 1 second. So this is actually a comparison of a space instrument from batch, Peppersax, Z2, SWIFT, Fermi, and then the UFO Lomonosov here. So this is the kind of sort of summary of our instrument. Gamma X-ray energy range is, well, I will talk in a minute, but we are trying to lower our energy, well, down to 5 keV. And then the X-ray instrument is a little bit different from a conventional detector, which is CGT or cadmium telluride. But we are using the crystal called YSO. And then our detection area, this X-ray, our detection area is well, more than 20 times smaller than the SWIFT. However, we are not so bad because our field of view is pretty competitive. And due to a smaller area in the detector, so our localization accuracy is poorer, maybe factor several. So SWIFT is 1 to 4 arc minute, but in our case, it's about 10 arc minute, our localization accuracy. So we are able to see the UV optical as SWIFT. However, as I told before, the SWIFT response time is 60 seconds, but UFO Lomonosov is the 1 second. Okay, this is explored or accessible domain for the GRB study. This is time, response time, and then this is color. Well, this is IR, and this is UV optical, X-ray, and gamma ray. This is a blue, box is given by the SWIFT band and the SWIFT XRT. This is Fermi coverage. And then there are several, the ground telescope. They achieve they are actually the lower the color, very near the IR here. Also, this is SWIFT U-boat. So our instrument will lower this X-ray down to 5 keV, as I mentioned, and also in this region, this is very early time, below the 20 seconds. So we will cover all this time domain by the sling mirror telescope. Okay, so let me come to our instrument. This is UFO onboard Lomonosov. Actually, this is I would say pioneering mission to prove the concept of sling mirror telescope. This is response time is, I would say, this is 1 second. This is very small. This is 10 centimeter compared to the 30 centimeter of the SWIFT. However, actually, the measurement power is not really bad. Actually, I will show later. Also, I would say this is a sort of pathfinder mission for the future GRB mission. This is, we show the very early optical afterglow, and then we also need the very lowering the X-ray also. So Lomonosov spacecraft is following. Actually, this is a so-called medium, not small. I would say this is small satellite. About 5 kilogram payload is about 120 kilogram. There are 4 payloads on board. The first one is this. Actually, this is a main mission of this Lomonosov called the TOOS telescope. This is ultra high energy cosmic ray measurement, just looking down the Earth. This is 1.5 meter Fresnel telescope. On top of there are 3 payloads. One of them is UFO pathfinder for gamma ray burst, which I will talk in a minute in detail. Another telescope, another instrument for the GRB, this is BDRG. This is crystal, CSI crystal-based telescope. This is, I would say, this is look like a Fermi, the GBM-like. So there is the camera. This is a wide field of camera, shark. But their sensitivity is poor, but I think they have a very large field of view. So it gives some sort of help to study the gamma ray burst. Okay, this is taken several years ago. This is a platform built by VNIEM, and then there are here you see the TOOS telescope. There are other 3 payloads here. So as I told you before, BDRG is GBM pyramid types. X-ray, this is a range of measurement. This is CSI crystals. And then the shark is optical observation, wide field of view, but the sensitivity is limited to 13. UFO pathfinder, this is SWIFT type. We have X-ray and the UV optical. Well, I will talk in a minute, and the TOOS. Well, this is chance is really extremely rare. But if you are lucky, we will see the ultra high energy cosmic ray together with the gamma ray burst. This is really whole, but with share. Okay, this is our instrument of the UFO, Lomonosov. There are two instruments basically. The UVAT, this is X-ray measurement, and the other is UV optical measurement. So this, okay, the overall weight is about 25 kilogram with the 25 watts. So this is quite small compared to all the famous missions in space. However, I will give you some our specification or expected performance in the later. I think we are not so bad. Okay, so first I will talk about the UV optical instrument. This is a slewing mirror telescope. Here you see this is a nominal rich cretin telescope, 10 centimeter aperture. In front of that, we have a fast slewing mirror system here. So we are quite limited in the weight or mass required by Lomonosov. So there are a lot of technology to reduce the mass actually. So overall mass is less than 8 kilograms. This is really hard to believe anyway. So inside there is the rich cretin 10 centimeter aperture telescope. Well, actually this is built by Samsung. Because we have some of we need money, and then we ask them to build it anyway. So here there is a slewing mirror stage here, you see. So in order to reduce the mass, and then we have a lot of technology just digging out the backside, and then before making aluminum on top of that. So here you see this is response speed and angle. This is quite expected as we designed. Here you see our slewing mirror telescope point spread function. This is a 4.4 arc-second. This is actually similar to a Swift. So actually, we use the intensified CCD. This is identical to the Swift anyway. So I think I think all look identical except one. Just we have a smaller aperture as a Swift. So the slewing mirror, we have a slewing mirror here. This is pointing accuracy is measured to be a 2 arc minute error. So this is really within our the tolerance actually. And the settling time is quite fast. This is several hundred milliseconds. So I think in overall angle, we like the plus minus 35 degrees. So this is published by Optics Express, and then this is this paper was elected as a highlighted article that month. So we also we measured the point spread function. I think this is the same measurement as I told you before. This is actually timing to adjust our the location of our telescope, and then we end up with the about 1 pixel size. This is accuracy. 1 pixel size is our case is 0.5 arc-second. So we claim our UV optical accuracy is 4.5 arc-second. So sensitivity. Well, our sensitivity, we estimated about 19 magnitude for 100 seconds of exposure time. So this means we should detect the long duration GRB unless they are extinguished by a dust in their host galaxy or high redshift greater than 6. So here you see this is most of GRB as a function of magnitude at the time of about 86 seconds. Okay, but concerning the redshift here, so this is actually the Canada. This is collection of light curve here, and then this is 19 magnitude here, and then the 5 or 6, 17 magnitude. If this GRB is at the place of redshift 10, however, certainly what you need is such a instrumental the capability. Otherwise, you can't measure. However, also there is a Lyman limit. So in our instrument, we hoped to measure the GRB up to redshift 6. Because above the 6, so we can't because of a Lyman limit. So basically, we say I think most of region. If GRB is not really, not the one we expected, but we like to observe. I think most of GRB we think. So specification of our 3-meter telescope here. This is a list of, okay, this is basically same as Swift here, but the aperture is different. They have 30 centimeter, we have 10 centimeter, but all are quite similar. So that's why our sensitivity is lower, probably a factor 2 or 3 than the Swift. But we are not competing with the Swift. Basically, we are looking at the early time domain. So early time domain, we hope the luminosity is much stronger than the later time. So I think we hope we will do a good job anyway. So let me come to the X-ray instrument. This is we call the UFFO, UFFO telescope. We are based on the coded mask technique as Swift. Here you see some detectors underneath. Well, this is the principle is the same as Swift, but this the field of view. This is actually design values. Field of view is 90 by 90 degrees. Source position accuracy is about 10 arc-minute, and then we expected our detector working above the 15 kV, but let me show what we measured. So processing time is a few seconds. This is actually the designed value. We choose the coded mask. This is not the random coded mask. This is actually two-dimensional random coded mask designed by a Spanish group. And then we use the detector, as I mentioned, YSO crystal with the multi-anode PMT with electronics. So this is a simulation done by a Spanish group. I hope this will work, but well, this is basically actual, background in the sky. This is 90 degree and 90 degree, and then the collection of light as time goes on, and then this is the result of our analysis. So at the late time, you see the very nice localization of GRB. Okay, so this is also simulation. This is in terms of arc-minute, 0. So this is more or less plus or minus 8 arc-minute. I think most of GRB contained within this accuracy. That's why we call our UFFO accuracy is 10 arc-minute. The Swift is about 4 arc-minute. So this is a coded mask, and then if we look at this is just a random mask, and then if we look at the inside detector, and then you see the very nice, the mask on top of the detector. The detector is here like that. This is the overall, the area of detection area is about 200 square centimeter, and then the YSO and crystal and MAPNT are integrated here with analog board and digital board and so on, and then we successfully integrated all the device, and then we deliver this very beautiful, the detector to the Moscow. So before, actually last year we delivered our instrument to the Moscow Space Agency, and then we have another set in our country, and then we tested it. This is we call the UFFO by using the X-ray mini tube from the George Smoot Labs. So we followed this mini tube, and then we tested it. And then this is the actual result. And then this is we are clearly seeing our source. Of course, the source rate is somewhat larger than we expected. Actually, typically 10 kV or 15 kV, we expect 1 square centimeter per second, 1 photon X-ray with the 2 or 3 diffused background. But in this case, we illuminate much more source. So that's why we see it very clearly. However, we did again. Actually, the source and the background rate is almost similar. So this is here, you see the source is a 1.8 count, background is about 1.1 count. But let me notice that this is actually, the not official, slide, but in this test, we use the very sort of this type of detector because our so-called flight model is already delivered to the Moscow, so we cannot touch anything. So we have a second set we call the pre-flight model, but here, actually some of PMT were not there, and some of the electronics were not running properly. So I would say maybe overall all channel, out of all channels, maybe 30% doesn't work. But however, we have a very nice result. So this means we are quite confident our flight model will work better. Another thing we did in our lab test is following. We illuminate X-rays with particular energy, for example, the 8.6 and so on. This is some part is the molybdenum, some part usually amelioration source, or these are using the X-ray mini tubes with using some filter here. So we eliminated such a particular energy, and then we got the result as follows. So here you see the 60 keV, we have very nice peak, 28, 21. So even 8.6 keV, we see the very clear peak here. So this means, well, this is about 40% of energy resolution. So we are now, what we are doing is, we like to do test, the same test with the very low energy X-ray source. So what we have is only ion source, which has 5.5 keV. So now it's in progress. So from this figure, we like to confirm we are able to see X-rays of energy down to 5 keV or even less, probably 4 or 5 keV. So this means this is very important for our UBEN instrument, because this means we can see the high redshift gamma ray burst. Even though we don't see the optical, but we can give you a lot over such a very high redshift gamma ray burst. Another, another item I like to notice you is the following. All readout and trigger, everything is done by a so-called FPGA. We don't use any CPU like Swift. So this means trigger latency. This is so-called rate trigger and imaging trigger. Everything all done is done at the FPGA. So we are very fast. So typically our trigger, so-called trigger latency before giving a trigger, this is test 100 milliseconds. So this is very negligible. So this is depicted here. So we should wait X-ray about at least 1 second, because we have a smaller area of detector, 20 times smaller than Swift. However, at the same luminosity of GRB, Swift may have 25 times faster. So 1 second, 40 milliseconds, same amount of X-ray hitting our detector, and then trigger calculation is done by 100 milliseconds. However, the Swift takes several seconds because they are using the CPU. So our thrilling speed is 1 second, and then Swift is about 100 seconds. So this is what we will do all the processing. So typically about 2 or 3 seconds. So we can give you, for example, for the X-ray trigger, we can give you, in a second, we can give you the alert to the also ground telescope. So this is the parameter expected performance of UBET, the X-ray. This is UFFO onboard Lomonosov. This is Swift. While we are using crystal, they are using the Swift using cadmium zinc telluride. This is one of the famous material for the X-ray measurement, but we are using here. But our advantage is we are using the multi-anode MAPMT. This means we multiplicate all the electrons. This means we are quite insensitive to the noise compared to the cadmium zinc telluride, but we will see it. So that's why we can lower the sensitivity to the 5 keV. So we expect about 20 GRB every year compared to the Swift, but because we have the smaller detection area, also it also heavily depends on the orbit, but orbit has not been decided fully. But I think about 20 is more or less conservative limit. Even Bruce, you don't agree that. Okay. Anyway, so all instruments were delivered to Taiwan National Space Agency for the thermal vacuum shock vibration test. This is all done very successfully there. And then we delivered to the Moscow. NIEM is a space agency, Nikolai's here. And then we did so-called the final validation test at the NIEM. So we still have, this is a 3-meter telescope accuracy. This is still we have 4.3 arc second. And then the integration to the platform structure at the NEM at Moscow. Well, this is actually not kind of a mock-up model. This is basically the flight model. And then I believe this payload and another payload with the platform were delivered to VNEM at the Moscow downtown, I think the last month. So let me come to the summary. So the camera bursts are unique proofs of physics, including studies of early extreme and so on. Well, we like to explore the new time domain and also color. Well, not we like. I think everybody like to, explore the new time domain and the new infrared regime, increasing the sensitivity. So UFO will open a new time domain of GRB optical emission in the first few seconds and foresees triggers of high redshift GRB with a faster large to the ground robotic telescope. So UFO Lomonosov will be launched in 2004. And then I'd like to thank all our collaboration here. So the Korea and Spain, Moscow, Taiwan, and so on. Thank you.